You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Amir Siraj. Amir studies astrophysics at Harvard University and is interested broadly in theoretical astrophysics. He is a Goldwater Scholar and US Presidential Scholar. He is co-president of Harvard Students for the Exploration and Development of Space and former senior US editor of the Harvard Political Review. His research advisor is Professor Avi Loeb.
Amir Siraj, welcome back to the program.
Thanks, John. So happy to be here.
You've released a number of papers recently, and one of these deals with the mysterious Oort Cloud, the far outer reaches of our solar system. And one of these deals with the idea of long-period comets having been a strong possibility to have been the impactor that caused the Cretaceous Tertiary impact that killed the dinosaurs. Meaning that the Oort Cloud is deadly sometimes, and that we should pay attention to it even though it's far and distant. Now, what is the mystery that surrounds the impact that led you to formulate a sort of novel idea about a cometary breakup being responsible?
Yeah, so the origin of the Chicxulub impactor, which killed the dinosaurs 66 million years ago, is an unsolved puzzle. And it's mystified astronomers for decades. And the primary reason why is because of the recency of the impact combined with its composition. If we look at the asteroid belt and we look for, near-Earth objects that could impact the Earth, and we whittle down to the type composition we observed in the impact, which is carbonaceous chondrite, we wouldn't expect a Chicxulub-size impactor to hit the Earth of order 100 million, on the order of 100 million years, which we did, but rather on the order of once per few billion years. And it was quite a dramatic impact. It struck the Gulf of Mexico. It delivered more energy than a quadrillion tons of TNT, caused tsunamis, wildfires, a huge cloud of debris that enshrouded the planets and cooled the atmosphere. And as a result, most of the death resulted because of photosynthesis grounding to a halt. And as a result, 3/4 of species living on Earth at the time were wiped out. And I guess the first breakthrough in the Chicxulub problem was identifying the cause as extraterrestrial, as an impactor from space. And this was done by Luis Alvarez, who was a Nobel laureate in physics, and his son, the geologist Walter Alvarez. And they sort of made that causal connection between the Chicxulub crater and global extinction that occurred around the same time. And they did so in the 1980s. But to summarize the problem, there are two broad possibilities: asteroids and comets. And asteroids are rocky, comets are icy. Asteroids are close to the sun, comets are far from the sun. And we grew up hearing that the dinosaurs were killed by an asteroid, since there are more asteroids than comets that could strike the Earth at any particular point in time. But the key is that neither of the known populations of asteroids nor comets can explain the observed magnitude and recency of this catastrophic event while matching the general class of composition that the impact was observed to have, which is carbonaceous chondrite. So hence the mystery, what killed the dinosaurs? And there's been lots of speculation on the subject. The mainstream view is asteroid, and there was a paper about 10 years ago that blamed Chicxulub on the breakup of a main belt asteroid, but it ended up being inconsistent with both the timing and composition of the impact. And, that sort of sets the stage for the paper that I wrote with Professor Loeb.
Carbonaceous chondrites. are among the most interesting and mysterious meteorites that we have in our collections here on Earth. And that the carbonaceous chondrite also may have been responsible because we found amino acids in these things, right? I believe the Murchison or Allende carbonaceous chondrites. So that which may have given Earth life, and comets may have also delivered the water to Earth that we now enjoy, that which creates life takes it as well. And this is the Oort Cloud. The reality of the Oort Cloud is that very primitive materials that are created at the very beginning of the solar system sometimes come careening through. Now, what is the significance of a cometary breakup in this scenario? Meaning that it's not just simply a comet coming in from the Oort Cloud, but a breakup. What's the significance there?
Yeah, that's a great question. So since comets spend most of their time very far away from the sun, they're particularly sensitive to gravitational interactions with the sun and the planets. Much like how a great musician performing in a concerto with an orchestra is attuned to the musical gestures coming from both the conductor and the individual sections. And so what I showed in my paper that came out in January is that if you follow the orbits of comets through dynamical simulations, you find that a large fraction of all long-period comets, these ones coming from the Oort Cloud, experience this sort of epic journey through the solar system. And I guess the picture is that the Jupiter-Sun system shapes the orbits of comets that enter the inner region of the solar system, sort of like a pinball machine. And this pushes a fraction of all cometary orbits into ones that bring them very close to the sun. And during these passages close to the sun, the comets, which are nicknamed sun grazers, can experience very powerful tidal forces that break apart pieces of the rock and ultimately produce fields of cometary shrapnel. And in a sun grazing event, how it works is the portion of the comet closer to the sun feels a stronger gravitational pull than the part that's further from the sun. And this results in a tidal force across the object. Then you can get what's called a tidal disruption event, in which the comet breaks up into those smaller pieces. And what we found is, crucially, on the journey back to the Oort Cloud, there's an enhanced probability that one of these fragments hit the Earth. And so essentially you can think of it as these Chicxulub-sized cometary shrapnel are produced more often than just Chicxulub-sized comets or Chicxulub-sized asteroids. And as a result, we get an enhancement in the expected impact rate that one wouldn't realize from just staring at comets or staring at asteroids that we see in the solar system, because these swarms are produced too rarely for us to observe them.
This sounds awfully familiar, as in Comet Shoemaker Levy, where we saw Jupiter tear it apart before it hit. So this is not unprecedented. This is something that happens, that cometary breakups are, they're just loose conglomerates of ice and rock. So this isn't really saying anything that we haven't seen.
Exactly. And it motivates further sort of numerical simulations of how the physics of tidal disruption exactly works, particularly for chemically bound objects, or combinations of rubble piles and chemically bound ices, which is, quite frankly, still poorly understood. Comet Shoemaker Levy is one of the few examples we have of observational evidence. So both looking for more tidal disruption events that occur near the sun or near Jupiter, and performing more simulations of these events will allow us to understand what these fields of shrapnel look like, and as a result, get a better sense of the sort of long-term risks that our planet faces.
Right. So you're, I assume, going to test this by looking at sun grazer comets and as they break up, and basically look at the mathematics of that and learn just how often this sort of thing happens and what threat it poses, right?
Exactly. And, at the same time, we're also working with a team of scientists from Princeton University to investigate physical evidence produced in the Chicxulub event that could provide hints as to the composition and therefore the nature of the impactor and about possible future impactors. So we'll also be working with a team that is going to be applying the latest technologies in terms of chemical analysis of ejecta. And we'll just be following the science and seeing what we learn about nature in the process. And as you mentioned, it also certainly highlights the importance of understanding existential risks to humanity that we can address using the tool of science. And I think the pandemic has been a very sobering reminder of that. And my hope is that COVID-19 serves as an impetus for more forward-looking, proactive investments in science that can help us both understand and prepare for natural risks, whether they be future impacts or future pandemics or impacts from asteroids and comets.
Now, let me ask you this, composition. We suspect carbonaceous chondrite material. And I also know that with the Cretaceous Tertiary boundary, the KT boundary, there is an association with iridium, which is common metal in space, not so common here. What do you look for? What chemical elements and isotopes are you going to look for regarding that meteorite?
Yeah, so the issue right now is not so much, we wish we had that problem right now, but right now the problem is finding samples that are pristine enough to analyze. Unfortunately, there was only one really good sample of intact rock that was produced in the impact, and it was destroyed during the process of analysis. And so right now, we're trying to identify material that would simply be suitable to analyze that was produced in the impact. And so that's actually quite a difficult process and involved working with scientists from all over the globe at many of the major KT sites, because the science that we're trying to do and the level of isotope analysis that we're trying to do, it hasn't been done before with Chicxulub materials. And therefore the materials themselves pose a problem because we need to find pristine examples. But once we get our hands on the right samples, one thing we'll be looking for is to drill down the type of carbonaceous chondrite, because there are many different subcategories, and see if we can identify the subtype within that category. And that will help us in conjunction with future sample missions to comets. There have been many to asteroids, but very few to comets. And so sort of all of these lines of observational evidence at the same time should hopefully resolve this matching issue.
What of impact glasses? Did this event produce tektites that could possibly be of interest?
Yeah, that's tektites are definitely of interest to our observational team. So that's definitely something we're looking at as well.
Now, to switch gears, another paper that you recently authored was about the idea of interstellar objects in the Oort Cloud, passing through the Oort Cloud, outnumbering Oort Cloud objects themselves. Could you give us an overview?
Absolutely. So the Oort Cloud is an icy shell of debris that's located between 1,000 and 100,000 times further from the sun than the Earth. And its size sort of dwarfs everything else in the solar system, including the planetary region. Neptune is only about 30 times further from the sun than the Earth. The Oort Cloud is very interesting to study because, for one, we can't observe it directly because of how faint the reflected sunlight is on objects that far away. And secondly, because from what we do know about it, it should harbor far more asteroids and comets asteroids and comets than there are in any other region of the solar system. So how do we study the Oort Cloud? Well, the sun is like a street lamp illuminating a small patch of pavement around itself. And as a result, our search volume is quite limited, since the flux resulting from reflected sunlight scales with the fourth power of distance. As a result, we learn almost everything we know about the Oort Cloud by studying comets on highly elongated orbits, which clearly originated from the outer solar system, and then modeling the dynamical behavior of the inferred background population, most members of which never make it into the inner solar system. Now, the Oort cloud is quite tenuously bound to the sun, since it extends about halfway to the nearest star system, Alpha Centauri. And the low binding energies of Oort cloud objects means that they can easily be jostled out of their orbits, either by passing stars or the influence of the galactic tide, or even interactions with the giant planets. As a result, the Oort cloud is one of the most plausible sources of interstellar objects, at least from the point of view of our solar system's contribution to the budget of interstellar objects. But possibly if other solar systems have their own Oort clouds, exo-Oort clouds, they could too easily contribute pristine comets to the interstellar medium, and those might someday pass through our own solar system. So the funny story is, while the first interstellar object, called Oumuamua, looked nothing like a comet, or for that matter, anything we'd ever seen before in the solar system, the second one, named Borisov, displayed an uncanny resemblance to comets from our own solar system. So for the first time, we can do a one-to-one comparison of the relative abundances of solar system and extrasolar planetesimals, since we can estimate roughly how common interstellar comets are based on the discovery of Borisov and given the current reaches of our telescope. And we can compare this abundance with the estimated number density of Oort cloud comets based on observations of long-period comets. Now, near the sun, objects from the Oort cloud are definitively more abundant than interstellar objects. We have only detected one confirmed interstellar interloper since the first comet was detected with a telescope by Gottfried Kirch in 1680. But the key point that we make in our paper is that, hey, this is actually not generically true, but rather biased by our proximity to the sun. So as I mentioned, Oort cloud objects are quite tenuously bound to the sun and therefore represent a population with a low velocity dispersion. And in contrast to this, interstellar objects reflect the velocity dispersions of their parent stars, which is about 2 orders of magnitude greater than that of objects in the outer reaches of our solar system. As a result, the two populations undergo vastly unequal effects resulting from the gravitational pull of the sun. This is called gravitational focusing. And the result is that objects are attracted to the sun, or rather Oort cloud objects are attracted to the sun, sort of like moths swarming around a lamp, while interstellar objects whiz about the galaxy at high speeds and remain nearly impervious to the gravitational well of the sun. And the surprising implication of this is that out in the distant reaches of the solar system, in fact, within the Oort cloud itself, interstellar comets should outnumber solar system comets, or in other words, there should be more visitors than permanent residents in our own solar system. And while having interesting philosophical implications in its own right, this conclusion also sets exciting new constraints on planetary system formation processes, since it requires planetary systems to throw out orders of magnitude more mass than previously thought to give us even a remote chance of observing an object like Borisov. And the bottom line is that planetary system formation must be highly inefficient. And we're currently engaged in follow-up work involving Oumuamua and rogue planets as well that puts even stricter requirements on planetary system formation processes to produce the mass budget of unbound objects. And also from an observational standpoint, this paper has garnered a lot of interest from scientists searching for small bodies in the distant solar system, such as the stellar occultation surveys like TAOS, which can now expect to see significantly more objects, if they're able to see objects out in the Oort cloud than previously predicted.
One thing about the Oort cloud is the upper estimates on its size which I think are something around 200,000 AU, something like that. That reaches out far enough to open up the possibility that our Oort cloud is interacting with an exo-Oort cloud, that of the Alpha Centauri system. If the two systems are interacting, is it possible that our star systems are sneezing on each other and exchanging material out there, distantly in the Oort cloud? And by proxy, is it possible that there are interstellar objects that we captured from other passing stars over the history of the solar system?
That's exactly right. So the Oort cloud, since it is so vast and is comparable to the distances between stars, could very plausibly, well, for one, we know it must have lost much of its mass over the history of the solar system, just if you integrate the effects of the galactic tide and passing stars, etc., over 4.5 billion years. But indeed, if other stars have Oort clouds around them, like the stars right around us, these can definitely exchange objects as long as the objects are traveling just at the right speed in the right direction. But it's, I'm quite sure that our Oort cloud has many objects in it that originate from other Oort clouds, as you mentioned, that have passed close enough. So our Oort cloud already likely has a lot of diversity in terms of the bound objects because it exists at the edge of the solar system. Now, these are not going to be necessarily differentiable from a velocity standpoint, because the Oort cloud is spherical, so we wouldn't really be able to, make specific predictions about the directions that these should arrive from. And also, these would be bound objects, so they would be traveling at predictable speeds, both out there and near the sun. We could potentially observe differences in the sort of chemical isotopes that are expressed in the comets based on what we might expect from the sun's composition or small bodies closer to the sun. But the paper that I recently wrote holds true whatever is in the bound Oort cloud. We know how many objects there are, at least to order of magnitude. But rather, this is if you take all of the unbound objects, the ones that will only pass by the sun once, and compare them to the bound objects, the ones that will pass by the sun many times, hopefully, and the unbound ones should outnumber the bound ones. So there are likely both populations of unbound and bound interstellar objects in the Oort cloud, but the unbound population should dominate because it dominates over all of the bound objects, both interstellar and solar system in origin.
What is your take on the idea of a planet out there, Planet 9? And does that change the equation? Meaning that if you have the presence of, say, 4 Earth mass planet, a super Earth or something out there, does that change the equation on capture of unbound interstellar objects?
That's a great question. So I'm really, really excited for the eventual commencement of operations of LSST on the Vera Rubin Observatory, as many of my colleagues are as well, because this will solve so many cosmic mysteries. It's really beyond exciting. And one of the mysteries that it will help solve is Planet 9, whether it's really there or not. And Planet 9 is really exciting to me. I'm not sure if it's there or not. I think the only way of finding out is really doing this systematic search with LSST. But I've written a lot about Planet 9 because there are very interesting implications if it's there, and if it's there, what its origin was. If it was scattered from within the solar system, it was captured from outside of the solar system, or a number of other possibilities. And there are also interesting implications if it's not there. If Planet 9 is not there, and we continue to observe this weird sort of clustering out in the Kuiper belt, we'd have to explain that clustering somehow, whether it's a statistical fluke or the collective self-gravity of a really massive undiscovered asteroid belt, or one of the more fun possibilities, a primordial black hole. There's a lot of interesting science, no matter what happens with the sort of no matter what the observations tell us for Planet 9. But regarding capture, there are two sort of different possibilities here if Planet 9 does exist. One is, if Planet 9 exists, it could do exactly what sort of Jupiter does in our neck of the woods. And what Jupiter does is it acts in conjunction with the sun as a sort of fishing net for interstellar objects and interstellar material. And that was one of the earliest papers I wrote with Professor Loeb about captured interstellar objects. And there's been a lot of really great work on that since. But in principle, Planet 9 could do the exact same thing. It's less massive than Jupiter, but it would still definitely be helping the capture rate of interstellar objects. And those interstellar objects would have very specific set of orbits that we could search for. And so that's a very exciting possibility. And the second capture scenario is that if Planet 9 itself was captured, either it was a stroke of luck, because the probability of capturing a 5 to 10 Earth mass planet at that distance from the sun over 4.5 billion years is tiny, or the sun might have had a binary companion in the early solar system. And if that's the case, Planet 9 should not be the only thing that was captured, but in fact, it should have helped, that binary companion should have helped capture far more, dwarf planets and small bodies in similar orbits to Planet 9 as well. And we find that there should be about a factor of 20 difference between the lone star history of the solar system and the binary star history of the solar system in terms of the abundance of objects near Planet 9. And so if we find Planet 9 and also find a significant order of magnitude overabundance of dwarf planets and other debris in similar orbits, that could signal that maybe the sun did have a binary early on in its life. And that material would also be very interesting to go out and study, because that would be interstellar material, interstellar objects as well. But in that scenario, it wouldn't have been captured in the 4.5 billion years that has ensued since our sun left the birth cluster, but it would have been captured actually within the sun's birth cluster. And so that would be very interesting, because we could examine this really pristine material.
That's an interesting thought. Now, unlikely as this is, we do have what appear to be strong candidates for siblings of the sun from the same birth cluster, where these stars are so similar in composition that they must have formed nearby the sun. So it seems to me to be non-zero chance that we could actually identify the former companion of the sun if we ever saw it, right? Or does this have no legs?
No, so the sun and its siblings were all born from the same cloud of gas, which, as you mentioned, give them all similar compositions. And it's been really exciting to find stars with these really surprising compositional matches to the sun. I guess the disappointing thing for me is, even if the solar binary theory is confirmed in the future, the fact is that there's no way we could tell the sun's twin apart from its cousin or its uncle. In other words, there shouldn't be a compositional difference between the one that the sun happened to be gravitationally bound to and the next star over in the cluster that formed from the same cloud of gas. And so we can definitely, if we had the compositions of every star in the galaxy, we would definitely be able to identify the pool of stars from which our solar twin had to have originated. But I'm not sure that we could find the exact star that was, shining in the sky.
And plus, it could have been a red dwarf, which are very hard to study. So we'll probably never know. But it's interesting. Now, what of the idea of doing astrobiology in the Oort Cloud? Meaning that, is the pool of interstellar objects that could accumulate out there great enough to make it a more worthwhile place to look then within the inner solar system for evidence of an alien civilization, some defunct object.
Yeah. So, I mean, if we had the rocket technology to easily travel out there, I would be all for sending probes out to the Oort Cloud. But right now, it's quite difficult to do so. And also, if we even made it out to the Oort Cloud, the distances are so vast between objects that our best bet is probably staying near the sun and waiting for long-period comets to come by and studying their composition. Now, the disadvantage of this is that as they get heated up by the sun, their composition changes. But I don't think it's necessary to go out to the Oort Cloud to find interesting astrobiological implications, because we do have a plethora of long-period comets near us. Now, the interstellar objects is sort of another story, because I would say if LSST wasn't coming online with the Very Ribbon Observatory, we would have to sort of have a sort of large undertaking and fund stellar occultation surveys at a sort of new level, so we could enhance the rate of interstellar object discoveries to make it interesting, and we would also have to be working on our rockets. But the good news is that LSST should find a ton of interstellar objects in our own neighborhood, and that will be great, because then we'll be able to study them here if we have the necessary technology, and if we have a rocket that's ready and a payload that's ready, and as a result discover their composition, see what that tells us about extrasolar planetary systems, see if there are prebiotic or biotic materials on them. Another complementary method to this is searching for interstellar meteors. And that's actually one of the goals of the recently launched Galileo Project, for which I'm serving as the director of interstellar objects. And right now, we're currently in the process of designing a sort of mid-size, or a network of mid-sized telescopes, small to mid-size, that will systematically scan the atmosphere for any and all objects, so birds, planes, meteors, all the rest. And among the suite of exciting known phenomena that will detect, regardless of clarifying the nature of UAP, unidentified aerial phenomena, interstellar meteors probably take the cake in terms of holding the most secrets about the cosmos and what's beyond our solar system. We're talking about pieces of exoplanetary systems raining down onto the Earth that we would otherwise have to spend hundreds of thousands of years traveling to go get. So that's certainly one of the exciting aspects of the Galileo Project, in addition to the search for UAP. And this is especially true, I think, given that the only interstellar meteor discovery for an object larger than dust to date, which was made by myself and Professor Loeb, was from a government data set, and therefore the error bars are classified, which is really frustrating for science. That being said, Pentagon officials have expressed interest in possibly clarifying the nature of the error bars to reveal the true origin of the 2014 meteor. But it would be nice to have the capabilities to collect our own data for future interstellar meteors, and be able to do spectroscopy and go find the fragments on the ground. And what's exciting is that in terms of the budget necessary for interstellar meteor searches, we would need only 10% of the budget of the ESA Comet Interceptor mission, which might visit an interstellar object in the 2030s, if a suitable long-period comet candidate isn't found and a suitable interstellar object candidate is found. And so we could discover and retrieve a sample of an interstellar object here on Earth for 10% of the cost of the other sort of more obvious solution. And I should mention that also with the Galileo Project, we'll be searching existing and new data for interstellar objects using this upcoming avalanche of images from LSST. And in fact, we're actually hiring a postdoc named the Laukian Oumuamua Postdoctoral Research Fellowship to do just so. And while we're on the topic, I guess finding more interstellar objects like Oumuamua would be enormously helpful from a scientific point of view, specifically because there still isn't an explanation for Oumuamua that explains all of its properties. The latest attempted model, which tried to explain Oumuamua as a nitrogen iceberg chipped off of the surface of an exopluto, has a severe mass budget problem. And I wrote a paper showing that the amount of nitrogen necessary to produce such a population of interstellar objects exceeds the total amount of nitrogen locked in stars with 95% confidence, thus making the scenario untenable because only a small fraction of the mass in stars ends up in exoplutos. And actually, quite recently, there was a paper written by Levine, Cabot, Sligman, and Laughlin that reached the same conclusion about the nitrogen iceberg hypothesis through a sort of alternative analysis. And unfortunately, Oumuamua is too far away to observe and to do this follow-up study on, so we just need to search for more interstellar objects down the line. And finding large numbers of interstellar objects, as LSST will do, as hopefully the Galileo Project will do, won't just reveal secrets of individual objects like Oumuamua, but it will also allow us to do population-level statistics on interstellar objects, which have never before been possible. So this will clarify and refine the mass locked in interstellar object, which is important in terms of the constraints that it puts on planetary system formation processes, as well as the galactic inventory of heavy elements. And additionally, the distribution of arrival velocities and the directions of these objects will reveal the origins of interstellar objects at large, which I published a paper in the Astrophysical Journal Letters on. The idea is that if interstellar objects originate from stars, they probably do, their velocity distribution combines the stellar and ejection speed velocity distributions. And since ejection speeds are comparable to pre-ejection orbital speeds, they actually should reflect the region from which interstellar objects are likely produced within planetary systems. So now we're talking a sub-stellar level, a sub-planetary system level. And this information, in turn, is essential for understanding how interstellar objects are produced. High ejection speed should correlate with rockier objects from the cores of protoplanetary disks, while low ejection speeds should correlate with icier objects from the outer reaches of exoplanetary systems, perhaps from these Exo-Oort clouds. So interstellar objects from populations of stars other than our local thin disk population should actually also have clear kinematic signatures. And I wrote a paper about this, interstellar objects originating from stars in the galactic halo. And that's a whole different story. And halo stars are some of the oldest in the universe. So finding interstellar objects from a population like them could then reveal what some of the first planetary systems ever were like. So there's a lot of interesting science to be done, and I'm really excited about it.
In regards to Oumuamua and the LSST, so the LSST gets going and it starts looking, and presumably it should see a population of interstellar objects and be able to track them, and we'll see all kinds of stuff. What are the implications of never finding another Oumuamua? Say we turn it on, search, 10 years later, all we've seen are more Borisovs. Does that alter the equation of identifying or thinking about identifying Oumuamua?
Absolutely, yeah. So if we don't find another Oumuamua, but we find many other interstellar objects, that will bring our estimate for the number density of Oumuamua-like objects down significantly. And as a result, that will make the mass budget issues associated with a lot of the proposed explanations for Oumuamua, including nitrogen, including hydrogen, including light sail, etc. It'll alleviate a lot of these mass budget issues. But I think the problem is that it won't help us necessarily discern between the different scenarios. The only way we can really discern between the different scenarios, because they'll all be helped if Oumuamua is actually more rare than currently thought, is by finding another one and getting more data on it. or chasing down Oumuamua itself. But I'm not sure that we can say much more about Oumuamua, even if it ends up being really rare.
It could end up simply being, in one interpretation, an object a rare object that we've never seen anything like it and never see anything like it again. Or it's a wow signal, essentially, right?
Right, exactly.
Now, in regards to the Galileo Project and UAP, identifying the unidentified, what's that starting to look like? How are you going to do the search? What sort of sensors are you guys looking into?
Yeah, so right now our instrumentalist team is in the process of both selecting the suite of instruments that we'll be using, as well as starting to test some of the sensors that we're interested in. But what it will end up looking like is basically the first systematic search of the atmosphere for objects that pass through it. It's very similar to searches for meteors, but instead of simply being focused on fireballs and primarily observing at night, we'll be trying to catch anything that moves in the sky. And a lot of our observing will be during the daytime because that provides better conditions in a lot of respects than the nighttime for us. And so it's a very different equation from an instrumental standpoint than what is typically encountered in terms of building or designing astronomical surveys or arrays. And the reason that it's different is we are not looking at space, we're looking at the atmosphere. And as a result, even if you spend millions of dollars on a single telescope and you install the best optics you can find and have a huge mirror, etc., you are limited by two things. One is the distance between your sight and the horizon. You have a very limited view of the atmosphere. And so as a result, maybe you might be able to find small objects, but it's far too rare. Larger objects passing through the atmosphere are far too rare for you to ever find anything. And secondly, you might not even be able to find small objects particularly well because the atmosphere poses significant constraints on the seeing of telescopes, especially when you are looking towards the horizon rather than, closer to straight up. And our searches will be focused closer to the horizon because, of course, more atmosphere is located closer to the horizon than straight up. So we're still in the process of selecting and now starting to test the suite of sensors that we'll be using. But essentially, we're going to be looking to maximize our coverage of the atmosphere, to maximize our chances of observing something interesting, while at the same time employing a robust sort of scheme of not overloading ourselves with data. So maybe having a sort of follow-up, real-time follow-up system, and also building algorithms that can do a lot of the heavy lifting of filtering out planes and birds and drones, etc., out. So we can really look at the interesting things, whatever they might be, whether they're natural phenomena or something else.
Now, this also seems to me to be very useful in locating meteorite falls, right? So if you've got this all sky observation going, you could also search it for, interstellar meteoroids or even interstellar meteorites. Is it possible that sitting on this Earth somewhere, there is a meteorite of interstellar origin?
Oh, I'm sure of it. Yeah, absolutely. If you look at it from a statistical standpoint, there have to be pieces of interstellar matter. There are pieces of other exoplanets sitting on our planet right now, which is a mind-boggling thought in and of itself. But that is one of my goals, is to hold the first piece of an exoplanet in my hand. And I think that searching for interstellar meteoroids and interstellar meteoroids large enough to produce interstellar meteorites is likely the best bet. And so with Galileo Project, with the size of the network that we're looking to produce, we will be able to search for a gram scale interstellar meteoroids, which will be super exciting. And the holy grail of interstellar meteoroids would be the kilogram scale or larger, because those are most likely to leave behind remnants that we can go track down. And I've been thinking about this question a lot, and it's probably going to be, I guess, back in 2019 was when I first wrote a paper proposing that we build a worldwide network of interstellar meteoroid cameras. And so this has been on my mind for a while, and I think some of my future work will address the question to see if we can do this any more efficiently, or with fewer resources, or taking advantage of instruments that already exist. But it would be massively exciting. And by the way, the 2014 meteoroid was huge. It was much larger than a kilogram, the one that might be interstellar. And if it is confirmed by the US government, that would be insanely exciting. Now, why wouldn't we just go out and search for the debris from the fall? It actually broke up off the coast of Papua New Guinea. I would probably have to talk to some people who are more familiar with searches of the ocean floor, but I imagine it would be much more difficult to find pieces of meteorites than on the ocean floor than on land. But if the interstellar meteor is confirmed, we might want to search the ocean floor off the coast of Papua New Guinea.
Let's take this a little bit further into highly speculative territory. All right, so we have this mystery about a meteorite, Allen Hills 84001, that has an origin on Mars. And within this meteorite, there are structures that one team of scientists from NASA said appear to be fossilized microbes, evidence of microbes. So if we find an interstellar meteorite that has this same thing going on, that may actually have remnants of extraterrestrial microbes in it, that's actually a non-zero chance that we could find that, right?
Yeah, I mean, if we found microfossils in an interstellar meteorite, that would be, that would change our worldview, right? It would change our view of religion, our view of what our purpose is, the origin of life, the origin of humanity. I think that would be one of the most far-reaching scientific discoveries in terms of its sort of philosophical implications. And it's not science fiction, I think is the point. It's definitely within the realm of possibility. And the fact of the matter is, we don't know how prevalent life is in the universe, but it's plausible that it could be extraordinarily prevalent. The only way to find it is to search and to collect as much data as we can. And so that would be quite an exciting possibility indeed.
And hence the Galileo Project and the interest in UAP, because if life in the galaxy is common, then that would mean that every so often intelligent life is going to happen. And we're proof of that. And that brings us up against the Fermi paradox, because if there's an alien civilization out there that's 1 million years older than we are, they're everywhere, or should be everywhere, or there's a reason why they aren't. And if they are everywhere, then maybe that is the explanation for UAP. If just one ends up being of alien origin, then the Fermi paradox dissolves. That's seems to me to be worthwhile to at least check, at least take a look and see, especially with all of the claims that surrounds the phenomenon, right?
Absolutely. And just from a standpoint of the scientific practice, it sort of baffles me. UAP are interesting from a purely scientific view. I mean, without even having to speculate on their origin, just their name. Unidentified aerial phenomena. Now, before the Pentagon report, if you asked me, if it was worth raising and spending millions of dollars on a systematic search of the atmosphere, I wouldn't know what to say, because I didn't know what the standard of evidence was. But ever since the Pentagon report, the Department of Defense has confirmed that most of the UAP sightings reference and measurements referenced in the report are probably reflective of real physical phenomena and not sensor errors. the Department of Defense was not able to identify these objects. So no matter what, we have something to learn if these are real physical phenomena. We don't even have to hope that it's extraterrestrial life, because we could discover new natural phenomena in the atmosphere that have nothing to do with life. Or we could discover man-made objects that have very advanced technology from like foreign adversaries, for example. Or we could discover extraterrestrial life. I mean, point is that without investigating, we'll never know. And we have a very good reason for investigating, which is a US government report that confirmed that these are real phenomena that are going on. So it sort of baffles me when people sort of make comments saying that, oh, why should we look at the atmosphere? There's nothing new to learn. Well, there's a lot new to learn. And if we bias ourselves before we look, and that can take the form of saying, oh, there's nothing new, it's not worth it, we know everything that's in the atmosphere. And that can also take the form of being sure that it's one of the possibilities, like saying, oh, I'm sure it's aliens, or I'm sure it's ball lightning, or I'm sure it's whatever. None of those, I think, are particularly compelling points of view, because they sort of take the form of motivated reasoning. But from my standpoint, let's do this search and see what we find. We can only gain.
Yeah, sure. Yeah, I mean, no matter what, you're going to learn something. And even if it's just tracking interstellar meteoroids, it's worth it. And it's interesting to me, though, that if you look at the past scientists that have looked into the UAP phenomenon, back when we used to call it UFOs, they all came to really weird conclusions. And one of them was Donald Menzel, one of your Harvard people. And he was nagged. He thought that there was a natural explanation for all of them, but he was nagged by the possibility that there's some sort of atmospheric phenomena, natural atmospheric phenomena that we don't know anything about. And he suspected that might have been the case, but no one's ever really identified it if it is. So it's sort of interesting. And then, of course, there was J. Allen Hynek and McDonald, Dr. James McDonald. And McDonald believed that it was the alien origin was the least worst hypothesis. And that all the idea, and he was an atmospheric scientist, but he couldn't think of anything that atmospheric that could happen to reproduce it. So it's just this open wound that has been festering since World War II. The public wants to know what it is, and there's all sorts of content being created about it. Yet it has that stigma, as you mentioned, and I think that stigma needs to go away.
Exactly, and I think the way for that stigma to go away is by collecting more data. If we rely on existing data, on cameras from Navy planes or from eyewitness testimonies or any of the current evidence, right now there doesn't exist a clear image of a UAP. So it's very difficult to say what they are. That's why they're still unidentified. And I don't think the stigma is going to go away, because people will argue all day and call people names and get very emotional and angry about it. But I think the simple solution that we're trying to take and put forth with the Galileo Project is, we're not going to argue about previous data. In fact, we're not going to even touch that was previously collected, because we don't know the conditions under which they were collected. They were not collected by scientific instruments. Why don't we just do a systematic search? And if we find something interesting, it'll be done with scientific instruments, and we will know how they were calibrated. We will know how they were set up. We'll know exactly, it will be a very different scenario in terms of the data being collected. And we're going to go through the standard mainstream sort of peer review process and treat this just like any other scientific inquiry. I think so many people have been, I think the reason why Galileo Project didn't exist until this year is that most scientists who are interested are even afraid of touching the topic in the first place. So it's a sort of a self-fulfilling prophecy. But I think that the launch of the Galileo Project has shown, just simply from the fact of the caliber of our research team, which includes some of the top theorists and instrumentalists in astrophysics across the globe, it shows that there has been a lot of sort of latent interest, and there are a lot of scientists, very serious scientists, who have been wanting to tackle this problem for a long time and get to the bottom of it, whatever it might be, but haven't had the opportunity to until this project.
It truly is a stunning research team and advisory board, and it includes a friend of the show, Brian Keating, but also most recently Alan Stern and Paul Davies and many, many others. So if there is something to be learned here, it's going to be learned. And I find it exciting. Now, Amir, you also, my last paper I wanted to cover with you is alien communication and communication time. And you came to the conclusion in the paper that the most reasonable time frame we could expect a communication to us, a response to us, is about 3,000 years. Can you give us an overview of that paper?
For sure. So I guess the context is that, are we alone, is a question that receives a lot of attention. In fact, the entire field of the search for extraterrestrial intelligence, SETI, is dedicated to it. But a related sub-question rather, has received far less attention. And so we sought to answer it, which is, could we start a cosmic conversation? And if so, when might it be plausible? And the setup is this. Humanity has been leaking radio waves out into space for about the past century. And as a result, we've filled a sphere with radius 100 light years, give or take, with electromagnetic communications, which could potentially be eavesdropped on by an alien civilization within this volume of space. If such a civilization were interested in communicating with us, they could send a reply marking humanity's first cosmic dialogue with an extraterrestrial intelligence. And as time passes, the volume of space in which these putative extraterrestrial civilizations could hear us grows. So the chance that we might hear back increases. And so with Professor Loeb, I recently coined the search for such signals SETRI, or the search for extraterrestrial responding intelligence, and asked the question, when might we expect such a search be worthwhile? So the most optimistic assumption that one can make about the origin of intelligent life on Earth is the Copernican viewpoint, that it represents a single outcome of a random Poisson process that takes place on all Earth analogs and therefore is probably quite typical. And within that framework, the most optimistic Bayesian prior on the origin of intelligent life that one can use is the uniform distribution, since it favors values of order unity near 1 in a problem with an unknown scale. The distribution of technosignature extinction timescales can be inferred in a consistent manner through a Poisson process based on the influential formalism designed by J. Richard Gott in the 1990s. And then finally, we can sort of make the extraordinarily optimistic assumption that all technological civilizations within the path of one of our electromagnetic waves would respond. So putting all of this together, what do we get? Well, given that Earth has been radio communicating for only a century out of its few billion-year history, it's highly unlikely that an analog exists within the relatively small volume of stars encompassed by the furthest traveled radio transmissions. So we shouldn't expect a cosmic conversation, if you will, to start now. And it turns out that this only starts to change after at least 3 millennia, when the volume spanned by humanity's signals and the prior for the age of radio communicating civilizations are great enough that this optimistic limiting case, this Copernican principle case, begins to return non-negligible probabilities. So this means that we'll have to wait at the very least 3,000 years to hear back from an extraterrestrial civilization. And so the lesson that I learned from writing this paper is that we'd better get our act together and figure out how to survive long term if we ever want to participate in a cosmic conversation, which I certainly think we should. And we also investigated the possibility receiving physical probes from extraterrestrial civilizations in response to our radio communications. And physical probes are slower than electromagnetic radiation, obviously, but they can travel at a variety of speeds, from conventional rockets, which go at 0.01% of the speed of light, to subrelativistic light sails, like those proposed in Breakthrough Starshot, which move at of order a tenth of the speed of light. And we found that we'd have to wait at least 1 million years before we could start to expect the possibility of receiving a physical probe traveling at the speed of a conventional rocket that was sent in response to our technological existence, but only about 10,000 years during which receiving a subrelativistic probe in response to our communications would be implausible. So the bottom line is that if we wish to engage in a cosmic conversation with a civilization like our own, with physical objects, we'd really have to focus on our long-term survival as a civilization.
Now, my last question to you deals directly with the Copernican principle. So we spend, say, the next 500 years looking for evidence of technosignatures and biosignatures. And say, hypothetically, we see nothing, and it appears that we truly are alone, and the great silence persists. Do we then violate the Copernican principle? Does Earth suddenly become a privileged vantage point in the universe?
Yeah, well, this is an interesting and very sort of philosophical question. The sort of, you could say yes or no to this. So on one hand, you could say yes, it means that we're special because, you know, we must exist at a special place and a special time to be alone. But on the other hand, you could make the sort of an argument related to a weak form of the anthropic principle, which is that we are conscious observers. And so as a result, we wouldn't even be aware of our singular existence if we weren't conscious. So maybe the universe just produced one instance of intelligence, and the only reason that it seems special to us is that by definition we have to be observing the universe. So to me, it just seems most likely that under similar conditions you get similar outcomes. I think that is sort of, in my viewpoint, truer to the spirit of the Copernican principle, although I recognize that this is a philosophical conversation. So as a scientist, the best thing that I can do is go out and get more data and treat the analyses based on these different principles, whether it's the Copernican principle or the weak anthropic principle, which motivates the rare Earth hypothesis, as limiting cases in either direction. But I don't see a reason why similar conditions shouldn't lead to similar outcomes. And as a result, I would be very surprised if we don't eventually find both primitive and intelligent life eventually.
Well, it's worth noting that Seth Shostak, who's also on your advisory board, has openly said and openly bet human civilization that we'll find it within 20 years or he'll buy everyone a cup of coffee. So if SETI is that confident, I think we're going to find it pretty quickly. And maybe it'll be the Galileo Project that does.
Or we'll get coffee from Seth. Thanks
for joining us today, Amir. There will be links to all of the mentioned papers and the Galileo Project in the description below. And thanks for joining us again.
Thanks so much for having me. It's always a pleasure.
Anna, I have a surprise for you.
Is it another rock, John? A rock?
No, introducing Annabot.
So I am Anna.
Oh, well, that didn't work.
Oh, points for effort, though.
Indeed. So, what's for dinner?
Spaghetti, John.